Today for AI Paper Podcasts, we're looking at a paper that tackles what might be the single biggest bottleneck in training capable AI agents. The lack of a good gym to train them in.
Yeah, this one is a big deal. The paper is Agent World Model, Infinity Synthetic Environments for Agentic Reinforcement Learning, from researchers at UNC Chapel Hill and Snowflake.
And they've introduced something called AWM, Agent World Model.
Exactly. It's a pipeline designed to solve the data scarcity problem for agents that use tools. And the scale here is just massive. They synthesized 1,000 unique, fully executable environments.
1,000.
1,000. We're talking over 35,000 tools and 10,000 distinct tasks.
And just to be super clear for the summary here, these aren't just LLMs pretending to be an environment.
No, not at all. That's the key difference. Unlike older methods where one LLM hallucinates a world for another, AWM generates real functional code. These are environments backed by actual Scala-8 databases.
And they use the Model Context Protocol, MCP, to standardize it all.
Right. And the result is that agents trained in these synthetic worlds showed, really strong generalization to tasks they'd never seen before.
So they're outperforming agents trained in those LLM simulated worlds on benchmarks like, was it TauBench?
Yeah, TauBench, MCP Universe, the big ones. It's a significant step up.
Okay, so that's the 1-minute version. Let's really get into the weeds now. This whole thing is about solving the environment scarcity problem.
It really is. For Agentic RL, it's the elephant in the room. We don't have enough interactive software for these things to practice on.
It's not like AlphaGo, where you have a perfect simulator of the game.
Exactly. The rules of Go are fixed. But the rules for, say, booking a flight or managing a database, that's the messy real world. We don't have a perfect simulator for that.
And you can't just train a reinforcement learning agent by letting it loose on the actual internet.
I mean, you could if you wanted to go bankrupt really, really quickly.
Right.
You're left with two pretty bad options. Option A is using real-world APIs. You could try to train an agent on, the actual Expedia API.
But you'd hit rate limits in 5 minutes.
Instantly. It's expensive, it's slow, and you need authentication. You can't give an agent 50,000 credit cards to practice buying tickets. It's just not scalable for the millions of attempts you need for RL.
So that led everyone to option B, the LLM simulator.
Right, where you just ask a big model like GPT-4 to pretend to be the Expedia API, the agent sends a request, and the simulator just makes up a plausible response.
And this is where the paper draws a really hard line. They argue that whole approach is, broken.
Fundamentally broken, yeah. Because of state inconsistency. They call it the delusional feedback loop.
What does that mean?
Okay, so the agent tells the simulator, delete file X. The simulator says, okay, file X deleted. But then 3 turns later, the agent asks to list the file.
Yeah, simulator forgets and hallucinates that file X is still there.
Exactly. So the agent isn't learning causality. It's not learning that its actions have permanent consequences. It's just learning how to manipulate the simulator's text generation.
So AWM's approach is totally different. Programming-based synthesis, they call it.
Don't simulate the world, build the world. That's the core idea. They treat making an environment like a software engineering project. You build the back-end logic, the database, the API, all in actual code.
Okay, so let's walk through that pipeline. Generating 1,000 working web apps automatically sounds like a total nightmare.
It does, but they streamlined it. Step 1 is the seed. They started with about 100 popular domain names, Spotify, Amazon, stuff like that.
And big ones.
Yeah. Then they used a self-instruct technique to expand those into 1,000 distinct scenarios. So Amazon might become Pet Crate, a pet supply subscription service, or Ghost Kitchen OS for managing virtual restaurants.
But they didn't just take any idea that came out right. There was a filtering step.
A very important one. They used an LLM classifier to specifically filter for scenarios that support CRU'd operations.
Create, read, update, delete.
Right. They tossed out ideas for news sites or wikis.
Because there's nothing for the agent to do.
Yeah.
It can't change the state of a news article.
Precisely. To learn, an agent has to change the world. It needs to create a user, update a playlist, delete an order. A static environment gives you no reinforcement signal.
Okay, so 1,000 CRUB-ready scenarios.
Yep.
Next up is generating the tasks for the agent.
Yep, they generate 10 tasks for each scenario, and the main constraint was that the tasks had to be solvable through an API.
So no clicking buttons on a user interface. This is all about tool use.
All tool use. And they also made the assumption that the user is already logged in.
Skipping the boring part.
Yeah, we don't need the agent to spend 10,000 steps trying to figure out two-factor authentication. Let's get to the actual business logic.
Now for step 3, and this is where I think the engineering is really cool, the database. Most benchmarks just use a simple key value store, don't they? Like a JSON file.
Usually, yeah. Which is fine, but it's not very realistic.
Yeah.
AWM builds a full relational squeal-eyed database for every single one of those 1,000 environments.
With a proper schema and everything.
A proper schema. Tables, foreign keys, data constraints. This is so important because it means the world enforces rules. You try to put a string where an integer should be, Squillet will throw an error. The world actually pushes back.
And they didn't just generate empty tables.
No, and that's key. That's the cold start problem in testing. You can't train an agent on a task like cancel the order for the headphones if the orders table is empty.
The agent has nothing to work with.
Exactly. So the pipeline also generates insert statements to populate the world with realistic synthetic data. The music app starts with artists and playlists already loaded. It feels like a lived-in world from the start.
So we have the data. Step 4 is the interface. You can't just let the agent run raw SQL commands on the database.
Definitely not. So they synthesize an API layer on top. They use FastAPI and School Alchemy to build the actual endpoints. But the secret weapon here is integrating the Model Context Protocol, MCP.
MCP has been popping up everywhere lately.
It's becoming the standard, for good reason. By using it, they created a single, unified interface for the agent. It doesn't matter if it's talking to PetCrate or Ghost Kitchen OS. It uses the exact same list tools and call tool functions.
It abstracts all the connection logic away.
Right. So the agent can just focus on figuring out the tool logic. And I have to mention their self-correction loop.
Because the LLM is writing all this Python code, and LLM code has bugs.
Always. It might import a library that doesn't exist or just mess up the syntax. So they built a simple debug cycle. If the generated environment code crashes when they try to start it up, they just take the error message.
The traceback.
Full traceback, yeah. And they feed it right back to the LLM and say, hey, you got a module not found error on line 12, fix it.
And it works.
It works surprisingly well. They got over an 85% success rate with just over one retry on average. Turns out LLMs are actually pretty good at debugging their own code if you just show them the error.
So we have the gym. We have 1,000 working environments. Now for what feels like the hardest part of Agentic RL. How do you know if the agent actually succeeded? The verification.
This is the real special sauce of the paper because verification is so tricky. Let's say the task is create a playlist called Gym Jams.
Okay, the simple way would be just to check the database, right?
Mm-hmm.
Before and after. If there's a new row in the playlist table, it worked.
That's code-only verification, and it sounds foolproof, but it's really brittle.
Why?
What if the Gym Jams playlist already existed? The agent tries to create it, the API handles that gracefully, maybe returns a playlist already exists message. The database state doesn't change at all.
So the code-only verifier sees no change and marks it as a failure.
Even though the agent did its job, it ensured the playlist exists, it's the idempotency problem.
Right, so people try the other extreme.
Yeah.
Just ask an LLM judge.
Yep. Just feed the whole conversation to GPT-4 and ask, did the agent succeed? But then you're right back to the hallucination problem. The agent could just lie and say, I deleted the file, and the judge might just believe it.
So AWM's solution is a hybrid.
Exactly. They call it code-augmented LLM as a judge. They have a Python script that gets the hard facts by diffing the database. It finds things like row 45 was deleted or this value changed from X to Y.
So it gathers the evidence.
It gathers the ground truth, and then it feeds that structured evidence along with the agent's conversation to the LLM judge.
I see. So the judge uses the database truth to ground its reasoning, but it uses its language understanding to handle the tricky edge cases.
That's it. It knows the database didn't change, but it can also see why, because the playlist already existed. And it can rule correctly that the agent succeeded. It proved to be by far the most robust method.
That's a really clever solution. Now, speaking of rewards, let's touch on the training setup. They used an algorithm called GRPO, but what really stood out to me was the history-aware training.
Oh, this is such a practical, important detail. Usually when you train these agents, you give them the full history of the interaction.
Infinite memory.
Right. But when you actually deploy the agent in the real world, you can't do that. Context windows are finite. Tokens cost money. You almost always use a sliding window where you chop off the oldest messages.
So there's a mismatch. The agent gets amnesia in production that it never experienced during training.
It's a huge distribution shift. The agent tries to refer to something that's already scrolled out of its context. So what AWM did was align the training with that reality. They actually chopped up the training data into the same kind of sliding windows.
They forced the agent to learn to operate with limited memory from day one.
Yep. It forces the agent to learn better strategies. It can't rely on scrolling up to find information, so it learns to recheck the current state of the world if it's unsure about something. It makes the final agent much more robust.
That's one of those details that just screams, we've actually tried to ship this stuff. So the big question, does it all work?
The results were pretty definitive. They tested AWM-trained agents against a simulator, baseline agents trained in those fuzzy LLM-imagined worlds, and the AWM agents consistently won.
Which proves the core hypothesis. Interacting with a rigid, code-driven world with real consequences is a better teacher than talking to a hallucinating simulator.
It seems so. The database consistency forces the agent to be precise, but for me, the most impressive result was the generalization.
Right, because they trained on these fake apps like PetCrate.
Exactly. But they tested them on MCP Universe, which is a collection of real-world tools.
Tools for things like managing files, GitHub, financial data.
Yes. Real useful tools. And the AWM agents performed best in class. They could generalize their skills from the synthetic training world to out-of-distribution, real-world tasks they had never seen before.
That's amazing. It suggests the underlying skill of tool use is universal.
I think so. The basic logic of list the available tools, check their arguments, call the right one, handle the output is the same whether you're booking a fake appointment for a dog or deploying a real server.
It's the wax-on, wax-off effect from the Karate Kid.
That's a perfect analogy, actually. You learn the fundamental motions in a safe, controlled environment, and then you could apply them in a real fight.
Did they do an analysis on the scale? Like, does training on 1,000 environments really help more than training on 10?
They did. They trained models on sets of 10, 100, and 526 environments. And the performance just went up monotonically.
So more is definitely better.
Way better. If you only have 10 environments, the agent can just memorize the solutions. It overfits. But when you scale up to hundreds of diverse worlds, it can't just memorize. It's forced to learn the general algorithm of how to solve problems with tools.
And since the whole pipeline is automated, there's no real limit. They could generate 10,000 environments if they had the compute budget.
Right. And they mentioned the generation cost is pretty low, something like $60 per 100 environments. The bottleneck really just becomes the cost of training the agent itself.
This feels like it shifts the whole paradigm. We might be moving from an era of data scarcity for agents to one of environment abundance.
I think that's the big takeaway. We can engineer our way out of this data bottleneck. We don't have to wait to scrape more human trajectories from the web.
What are the limitations here? These worlds are still pretty static, aren't they?
That's the main one. The database only changes when the agent performs an action, but the real world is dynamic. Stock prices are moving, new emails are arriving, other people are booking the same flight you're looking at.
So the next step is building living world models.
Exactly. Multi-agent environments or environments with background processes that change the state on their own, that's the next frontier of difficulty.
Still, as a foundational piece of work, this is huge. And they released everything, right?
Yes. The pipeline code and all 1,000 environments are open source. Right now, it's the largest open source collection of tool use environments out there.
That's incredible for the research community. If you're listening and you work on an Agentic RL, this seems like a repository you need to check out.
I would, yeah. And I'd specifically look at their implementation of the code augmented judge. That verification pattern alone is worth its weight in gold. I fully expect to see that become a standard practice.
It really feels like the field is maturing from just prompt engineering to environment engineering. We're not just whispering suggestions to the model anymore. We're building an entire university for it to attend.
A university with very strict exams and no grade inflation. That's how you get capable graduates.
I like that. Well, if you want to check out the curriculum for yourself, the paper is Agent World Model.
A must-read for anyone in this space.
And that's our look at AWM for this AI Paper Podcast. Thanks for tuning in.
Keep experimenting.